Okay. Next, what we want to talk about is factorials. You may have seen these in been introduced to factorials in another math class. If not, it's not a big issue, but we will use factorials sort of in the binomial theorem, so we need to practice some of them before we get to that. So we need this sort of as a foundational understanding before we get to the actual binomial theorem. All right, so factorials. So it looks like an exclamation point. So 5 exclamation point just means you're going to take 5 and multiply it by every number below it, down to 1. Obviously, we're not going to multiply by 0 because then it would just be 0. So 5 factorial is the same as 5 times 4 times 3 times 2 times 1. 5 factorial is 120. So some of these you're just going to know. I would probably suggest that you memorize everything up to like maybe 7 factorial, maybe 6 factorial. The more you know, the more of these you know, the easier it's going to be and the faster it's going to be. All right, so 1 factorial clearly is just 1. N factorial, so we don't know what n is, but if we just wrote n factorial, we would think of that as n times 1 minus n times 2 subtracted from n times 3 away from n, and so on, and it would decrease and decrease until eventually you get down to 3 times 2 times 1, 1 being always the last number. Now, of course, you might say, well, what if n is 2? Well, of course, obviously you wouldn't have this many terms, but n, when we think about n, just think of it as a really big number, 10, 15, something like that. So, you know, if n is 10, then that's 10 times 9 times 8 times 7, eventually getting down to 3, 2, 1. So n factorial sometimes will expand out like this. Yes, if n is really small, like 3 or 2, then obviously you're not going to have this many terms. But we're going to think of n as just being a rather large number, and then we can kind of write these terms out. Okay. 0 factorial, just by definition, is 1. It'll become more clear why that is and why it would have to be later on when we do some more examples. But you just need to memorize that 0 factorial is 1. All right, so 6 factorial. So 6 factorial, I give you this answer. That's the same as 6 times 5 times 4 times 3 times 2 times 1. But a faster way of thinking of this is 6 factorial is also the same as 6 times 5 factorial. So 6 times 120, obviously 720. But you can think of it this way as 6 times 5 factorial. All right, so sometimes it's a little faster, and you'll want to think of it that way in a minute. All right, so 2 factorial, well, that's just 2 times 1. 2 factorial is just 2. 4 factorial, that's 24. 3 factorial is 3 times 2 times 1. Sorry, not 6 factorial is actually 6. And now let's think about this. What is 9 factorial over 6 factorial? Well, we could write it all out, right? This is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then 6, you know. But it might be faster to think of this as 9 times 8 times 7 times 6 factorial over 6 factorial. So now I can cancel out my 6 factorial with my 6 factorial. So 9 factorial is really just the same as 9 times 8 times 7. And of course, that, if we pick up a calculator, that's just 504. Okay, so just a little bit quicker and easier if you can think about reducing these, and that'll come in handy when we get into some of our binomial theorems that we need to talk about. Okay, so 7 factorial over 6 factorial. What could we write that as? Clearly, that's just 7, right? Because we could think of this as 7 times 6 factorial over 6 factorial. 6 factorials cancel. So, I mean, this works. You can cancel these kind of things. You know, just happens to be that several examples we talked about has 6 factorial in them, but it's not just 6 factorial that cancels. It's any factorial will cancel. So here, how would we do this one? Think of this as 9 times 8 times 7 times 6 factorial over 6 factorial. 6 factorial times 3 times 2 times 1. 6 factorials are going to cancel. We can cancel some of these things. The 3 cancels with the 9, gives us a 3. 2 cancels with the 8, gives us a 4. So everything downstairs canceled. So there's 1 in the denominator. 12 times 7. This one's 84. All right, so try the next one. Maybe without even writing it all out. Cancel out the 4 factorial with the 4 factorial up in the 8 factorial. So this will give us 8 times 7 times 6 times 5 over 2 times 1. So I've already canceled out the 4 factorials. 4, 3, 2, 1 upstairs got canceled with the 4 factorial here. And now we just want to reduce. Let's see, I guess I could cancel the 2 with the 2 and the 6 and give me a 3. So this ends up being 840. All right, next one. Try that. All right, so I'm going to cancel out 6 factorial with the 6 factorial up here. That gives me 12 times 11 times 10 times 9 times 8 times 7 over 6 times 5 times 4 times 3 times 2 times 1. You could, of course, leave off that 1. Canceling a bunch of things upstairs and down ends up giving us 924. All right, now sort of going in reverse, how could we use a factorial to write this? Clearly, that's just 6 factorial. Okay, what could I use to write this one? Clearly, this is going to be 6 factorial. This is just like the beginnings of 6 factorial, only a 3, 2, 1 is missing. So that means what has to be downstairs? 3 factorial. All right, so try that for this one. All right, so this is the beginning of 15 factorial. So on upstairs, I'm clearly going to have 15 factorial. On the bottom, what's the first thing that's missing? 13. 13 factorial is missing out of the 15 factorial. So that means we'd have to have 13 factorial on the bottom to cancel that out. All right, now try it with variables with an n. And again, assume n is large enough so that you would have this many terms. All right, so this is what looks like n factorial up on top. On the bottom, one thing's missing, so just like here, the first thing that was missing out of the 15 factorial is what's on the bottom. So the first thing missing here is n minus 4 factorial. So be careful, this cannot be written as n minus 4 factorial. That's very different. If you mean the factorial of n minus 4, you need to put that in parentheses. Otherwise, this is n, just the normal n, minus 4 factorial. So this is the same as n minus 24, which is not what we mean here. So be careful about parentheses. You need parentheses around there. All right, on page 2, we want to sort of tie these two ideas together. So we're going to ask you to expand the following binomial. If I could get you to include every exponent, even if it's a 1 or a 0, and every coefficient, even if it's a 1. So do that, include every exponent, every coefficient. Like for example, I'll start with, this is x plus y raised to the 5th power. So I'm going to start with a 1. I'm going to say x to the 5th power y to the 0. So do that and include all 6 terms, all 6 coefficients, all sets of exponents, even if they're a 0. Okay, so you probably used Pascal's triangle and used your 1, 5, 10, 10, 5, 1 row Notice the exponents on the x are decreasing by 1 every time. Remember that the exponents on the y are increasing by every term by 1. All right, so now what I would like you to do is use your factorials and come up with these numbers. Notice there are 1, 2, 3, 4, 5, 6 that I'm asking you to do. Do those now and see how, if you can see the pattern and see how this relates to what we just did. So you see that instead of using Pascal's triangle, instead of using this thing, which is a little bit cumbersome, especially if we wanted to go down to, say, the 10th or 11th or 12th row, it could be kind of cumbersome. What we could do instead is use these factorials to come up with the leading coefficients of our expanded binomial. All right, so the what we call the binomial coefficient. So this is the formula for coming up with these terms that we could otherwise get from Pascal's triangle. So we call these coefficients because they're the coefficients of our expanded binomial, and the binomial because we're talking about two terms that we're raising to a power. So binomial coefficients. So we used 5 factorial, for example, in one of them, right? In this one here, we did 5 factorial over 1 factorial, 4 factorial. Another way of writing that is, and this is going to be referred to in mathematics as a combination. So that's why we're getting a C here. We'll see this. We'll use it as a combination in probabilities later in the chapter. But it's a combination of what we call 5 choose 1. So that terminology will make more sense later on. And so another way of writing it is with like a parentheses, but there's no fraction bar here. It's just 5 over 1. So this is a combination. We say it as a combination of 5 choose 1, combination of 5 choose 1. In general, we'll use n for the degree that we're raising the binomial to, and then r will be a value that corresponds to sort of like what term we're dealing with. So here we would read this out as a combination of n choose r terms. Again, we call it out the same way. This is a sort of looks like a fraction, but it's not. It's a combination of n choose r. And so the formula is n factorial over r factorial, and then the difference of the two factorial. Okay, again, the really important that we have those in parentheses before we apply the factorial. All right, so try expanding these out, and also coming up with what this is equal to, and then come up with what row in Pascal's triangle would we find that. So in other words, is it the first row, the second row, the third row, the fourth row? So to start this first one, let's do it together. So that's going to be n factorial over, and then it's going to be 5 factorial, and then the difference, which is 4 factorial. The difference in the two numbers, which is 4 factorial. And then we would like you to expand that, or simplify that. And so that will give us, I'm going to pick the bigger of the two numbers to cancel upstairs. So that'll give me a 9 times 8 times 7 times 6. The 5 factorial gets canceled with this 5 factorial. And that's over 4 factorial. I could write it as 24, but I'm going to do it as 4 times 3 times 2 times 1. All right, so let's cancel some of these. I'm going to cancel the 4 and the 2, cancel with the 8. The 3 would cancel, so these are all 1s down here. 3 cancels with the 9 and turns that into a 3. So this ends up being 126. And so then what row of Pascal's triangle would you find the coefficient? Well, this tells us kind of the row. The 9 tells us the row. So we're really in the 10th row, if you really want to think of that first row as the 0th row. So, you know, it's the row that has a 1 and then a 9 and so on. Okay? So do the other 3 there. All right, in this case, it's going to be 25 factorial over 24 factorial, and then the difference, which is 1 factorial. So almost everything in the 25 factorial cancels with the 24 factorial. The only thing left, 25. And that will be the 25th row, or if we want to start counting in the 0th row, then it would be the 25th row, or if you want to think of this as the 26th row, it would be essentially a binomial to the 25th power is when we would be using this calculation. All right, 25 over 25. To write it out, to be technical, it'd be 25 factorial over 25 factorial, and then times the difference, which would be 0 factorial. So you can see why, in this case here, why we really need that 0 factorial to be 1. It's the only thing that would work here. So this is going to be 1. So a combination of 25 things, choose 25 of them, is 1. And then this last one, 10 factorial over 3 factorial, 7 factorial. And again, we want to use the 7 factorial to cancel that. It will cancel more things, and that's 10 times 9 times 8 over 3 times 2. So let's cancel the 3 with the 9. That gives us a 3 and a 1. Let's cancel the 2 with the 8. That gives us 4. So this is clearly 120. Okay, and again, the 10th row. All right. So this is your homework. It might be good because the last couple problems are asking you to expand binomials. So let's just review a couple things here. We'll review these again in the next video, but just make sure that if I have something raised to the nth power, so x plus y to the nth power, there's n plus 1 terms. If this is 5, I have 6 terms. If this is 10, I have 11 terms. All right. The first term is always x to the n. The last term will always be y to the n. With each succeeding term, x exponents decrease by 1 and the y's exponents increase by 1. Now remember too that the y might not, y or x, I guess, either one of those could be a number or it could be a number with an exponent, a number with a variable. The whole thing has to be raised to those powers. All right, the sum of the x and y exponents for any given term must also equal n. We saw that before. That means, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, and so on. And then there's a symmetry. So if I'm looking for the coefficient using combination of n choose r, that will be the same as n choose n minus r. So in other words, 5 choose 1 is the same as 5 choose 4. We saw that symmetry here, right? 5 choose 0 is the same as 5 choose 5. It's 5 choose 1 is the same as 5 choose 4, and so on.